Hello, everyone. This is the video presentation for stacked filters, learning to filter by structure. My name is Brian Hentschel, and this is work I do with my co-first author, Kyle Deeds, and my advisor, Stratos Idreos. We're going to start by motivating filters through an example application, namely URL blacklisting. So here, a web browser such as Chrome or Opera is warning you that the website you might be trying to go to is possibly malicious. It commonly implements this using a filter, where the filter here lossily stores a list of dangerous URLs. And it lossily stores this list so that it can be of small size. The browser then asks the filter, is this website dangerous? And if the filter says no, you proceed directly to the URL. Whereas if the filter says yes, you go to a remote server to get a definitive answer on whether or not this is dangerous, and then either go to the web page or present the warning message. And the filter has two goals. One, to be of small size, and then two, to generate as few false positives as possible. And these goals also actually tell you when filters are useful. Generally, filters are useful when the local resource is space constrained. Here, we're trying not to use too much space on the local machine from just the web browser. And then two, calls to the remote resource are expensive. Here, we're trying not to make too many calls to the remote server. In general, you can see this use case across other applications. For instance, in RocksDB, we use filters to guard against disk accesses. And then in Bing, we use filters to guard against accesses to a machine learning model which ranks web pages. You can additionally see these in relational data stores, cryptocurrencies, and many more applications. And in general, because we care a lot about both the local space usage and how many calls are made to the remote resource, filters are a very active area of research. In particular, people are looking at the ways we can use workload knowledge to make filters better. So here, what we're going to show is that in stacked filters, we can use sets of past queries to achieve 100x better false positive rates and be robust to shifting workloads in case our workload knowledge is out of date or incorrect, and fast computationally. And both of these last two actually contrast with using a machine learning classifier to make better filters, as is seen in other projects such as learn filters. So how do stacked filters achieve these benefits? It achieves it by changing the way we look at the domain. So if you look at traditional filters such as Bloom filters, the assumption is that we have some set P that we're storing, in this case, the dangerous URLs, and some very large set N, which is much, much, much bigger than P, which is all the things we're trying to filter out. So in here, it's just all other possible URLs. And under these assumptions, if you want some false positive rate epsilon, you need to pay size that is inversely proportional to this false positive rate. And importantly, if you look at this equation, this is about as good as we can do under this type of analysis. You cannot get much better than our current results. The way stacked filters actually moves beyond this theoretical optimum is by changing the way we look at the domain. So here, we're going to actually break apart the negative set into NF and NI. NF is the frequently queried negatives, and NI is the infrequently queried negatives. And we're going to assume that this frequently queried set, negative set, is roughly proportional in size to the positive set, where we generally use a heuristic that can be up to 100x as large as the positive set. And under these assumptions, we add some very small space usage delta, but in return for this small delta, we essentially eliminate all false positives on the frequently queried negative set. And we retain the same false positive rate of epsilon on all infrequently queried negatives. So if we look at how this would work for a motivating example of URL blacklisting, if we take 10 million spam URLs and the 10 million most visited websites, these 10 million most visited websites contain almost all web requests. So eliminating all their false positives means that we would have practically zero false positives when using a stacked filter. And zooming out from URL blacklisting to more generic applications, the general scenario we're targeting is that the set of negatives can be much bigger than the set of positives, but the set of negatives that are commonly queried is similar in size. Again, using the heuristic that it's within 100x of the positive set size. So now let's see how stacked filters actually works through an example. As their name suggests, stacked filters consist of a stack of filters, but to differentiate the filters inside the stacked filter, such as a Bloom filter, from the overall stacked filter, we refer to these individual filters as layers. And then the layers are ordered L1, L2, L3, ... The layers are divided up into two types: positive layers, which contain items from the positive set, and negative layers, which contain items from the frequently queried negative set. Queries are going to proceed through the layers in order, and for each layer, if they're accepted, they move on to the next layer in the stack. And if they're rejected by a positive layer, the stack filter rejects the item. And if they're rejected by a negative layer, they're accepted by the overall stack filter. And what's going to happen is essentially during construction, elements are going to be inserted into deeper layers until they're rejected by the opposite layer type. And then they're queried in the same manner, essentially until they're rejected. And then depending on which layer type rejects them, either they're rejected or accepted. And I think a concrete example shows this even more, where here we use Bloom filters. And the basic idea is if you look at a set bit, you're accepted. And if you look at an unset bit, you're rejected by the layer. So we start by inserting the positives into layer 1 and then querying the negatives. So here, N1 and N2 would be false positives if this was just a generic filter. Instead, we pass N1 and N2 to the next layer, and then we insert these into layer 2. The positives are then queried against this layer, and if they're rejected, they're accepted by the overall stack filter. So this maintains that there are no false negatives from a stack filter. Finally, we do this again with the positives being inserted and the negatives being queried. Queries that are rejected here but weren't rejected at layer 1 are queries that would have been accepted by a traditional filter but are rejected by a stack filter as we want. And this double check is what creates, or triple check or quadruple check is what creates the advantage of stacked filters over a traditional filter. More concretely, if we look at the space trade-off versus the false positives that are created through using more and more layers, we see that we gain much better false positive rates without adding much more space. So let's say that each layer uses 10 bits per element and has a false positive rate of 1%. So this is what a normal Bloom filter would do. If we make the positive set and the negative set the same size, in layers 2 and 3, we add 0.2 bits per element. And this is because only 1% of items make it to layers 2 and 3. In return for this 0.2 bits per element, the false positive rate on NF drops exponentially fast. So it goes from 10 to the negative second to 10 to the negative fourth. Whereas the false positive rate on the infrequently queried negatives is essentially unchanged. And if we added layers 4 and 5, 6 and 7, ... we would see the FBR drops exponentially fast towards 0 for the frequently queried negatives, whereas the size would converge as a geometric series to something like 10.202. So essentially no more added space. And this trade-off is what makes stack filters work. The size is barely increasing, but the FBR is dropping exponentially fast for the set that we care about. So now we're going to look at experimental analysis using URL blacklisting. You can see other applications besides URL blacklisting in the main body of the paper. So here on the right, we see that the y-axis is the false positive rate, and the x-axis is the bits per positive element. You can see that there's a trade-off, which is that as we increase the number of bits per positive element, the false positive rate is decreasing. And the goal for all filters is to move to the bottom left on this graph. That is, you want to be using as little space as possible and have lowest false positive rate as possible. If we look at stacked filters in comparison to Bloom filters at a fixed false positive rate, we see that stacked filters use as much as 40% less space. And if we look at it in comparison to learned filters, they're still using 20% less space. Or alternatively, if we fix their space usage and look at the false positive rate, we see that stacked filters achieve an 100x better FBR than Bloom filters and a 3x better FBR than learned filters. Additionally, if we look at the computation time of stacked versus Bloom and learned filters, we see that stacked filters use essentially the same amount of computation as Bloom filters. This is because they're both hash-based, and the first layer actually rejects most items. Whereas in comparison, the learned filter uses a machine learning model, which is in this case a neural network and was run on a GPU. And even using the GPU, this is 184x slower than using hashing on a CPU as in stacked and Bloom filters. So we see that generally stacked filters achieve much better FBR, do 100x better than traditional filters, and they retain all the advantages of traditional filters. That is, they're fast computationally and they're robust to shifting workloads, remembering that we kept that false positive rate of epsilon on all infrequently queried negatives as well. You can see more about stacked filters in the paper, namely theory about when they're better than traditional filters, how to tune each layer, how many numbers of layers there are, etc. Adaptivity, where we gather the negative set adaptively at query time, and more experiments on additional applications. Thank you for your time.